Welcome back, everyone, for another deep dive. This time, we're going to try to unlock the power of Kolmogorov-Arnold Networks. You might know them better as CANs. They're a really interesting area of neural network research. This can be pretty fun.
I think so too. It's
Yeah.
really interesting how CANs are different. They have this unique approach. Instead of using fixed weights like we see in traditional neural networks, they've got these things called learnable functions. They're right on the edges of the network.
So it's kind of like the connections themselves are learning.
Yeah, exactly. And
Uh-huh.
these functions, they're called splines.
Splines.
Yeah, and they give the networks a ton of flexibility and efficiency, much more than you'd see in a traditional setup.
Okay. So where does this Kolmogorov-Arnold thing come into play?
Well, it all comes down to this powerful mathematical theorem called the Kolmogorov-Arnold representation theorem.
Okay.
And basically, it says that any continuous function, like no matter how complex it is, can be represented as a combination of a bunch of simpler single variable functions.
So it's like taking something super complicated and breaking it down into smaller bite-sized pieces.
Yeah, that's a great way to put it.
Okay. I like it. So how did this idea of using this theorem for neural networks even come about?
The theorem itself, like the math behind it, goes back to the mid-20th century.
Okay.
But using it to actually build neural networks, well, that didn't really emerge until a couple decades later. There was this first wave of research in the 80s and 90s that was looking at how to actually take this mathematical concept and translate it into like a working neural network.
Oh, interesting. Were they successful right away?
Not really.
Okay.
So while those early studies were promising, they ran into some pretty big computational challenges. Basically, they were just too computationally demanding. It made them hard to scale up for real-world problems.
I guess they just weren't quite ready for prime time?
Yeah, you could say that. They got put on the back burner for a bit.
Oh.
But in recent years, there's been a big resurgence of interest in CNNs. Things like advancements in computing power, new optimization techniques, they've all kind of breathed new life into this whole area of research. And so now we're seeing this like really rapid evolution of CANs, new variations, wider applications, and even integration with other kinds of neural networks.
Well, that's exciting. And it sounds like this is where our deep dive comes in, right?
Yeah, exactly.
We want to help our listeners understand what CANs are all about, how they work, all that.
Right. I mean, it's a fast-moving field, and it's good to have a solid grasp of the basics.
Yeah. Okay, so let's get into it. First, can we just take a look at the structure of a CAN? I know they have a layered structure, kind of like those traditional multi-layer perceptrons or MLPs, but the way information moves through them is pretty different, right?
Yeah, that's right. The paper actually has a really good illustration, figure 2, I think. It shows the layered structure of a CAN really well. Each layer has these matrices, but instead of weights, like in MLPs, they're full of those adaptable spline functions.
Okay, so those splines are kind of acting like the connections between the layers.
Exactly. And they're dynamically transforming the data as it flows through.
Okay. But before we go any further, I think we need to unpack these splines a little bit. What exactly are they? I know we touched on it briefly before, but what
Yeah.
makes them so important for CANs?
So basically, a spline is like a piecewise polynomial function. Think of it like a curve, but the curve is made up of a bunch of segments, and each of those segments is described by like a simple polynomial equation.
Okay, that sounds vaguely familiar from like way back in calculus class.
Right. And these segments are all smoothly connected. It makes this continuous curve that can capture really complex shapes.
So how do these splines actually work in a CAN?
So remember how in a normal neural network, you've got those weights connecting the neurons?
Right.
Well, in a CAN, you replace those weights with these splines. It's like you're swapping out rigid links with these flexible, adaptable ones.
Got it.
And the really cool part is the control points of the splines can be changed during training. So the network can kind of learn the best shape for each spline to fit the data it's seeing.
So it's like the network is molding these splines to fit the data perfectly.
Precisely. It can adapt to those weird nonlinear relationships that often trip up other networks.
That's pretty cool. But I'm guessing there's got to be a catch, right? Training a network with all these adaptable nonlinear splines,
Yeah.
it's got to be a beast to optimize, I bet.
You're absolutely right. Optimizing CANs is a big hurdle, and researchers are working hard to come up with solutions. It's a computationally intensive process, and you need specialized techniques to guide those splines towards the right solutions.
So like what kind of strategies do they use to wrangle these splines into submission?
Well, one of the most common approaches is gradient descent.
Okay.
It's a method where you iteratively adjust the parameters of the spline to minimize the error.
Okay, I've heard of that.
And there are all these different variations of gradient descent. Stochastic gradient descent, for instance, throws in some randomness to help the network avoid getting stuck.
Oh, interesting. So it's like shaking things up a bit to help the network explore new possibilities.
Yeah, exactly. Then there's the atom optimizer, which is a popular one. It combines the momentum of previous adjustments with these adaptive learning rates. It's a pretty sophisticated approach.
Okay. So it sounds like training these cans is a real balancing act. But before we get too deep into the weeds of optimization, I think we should address the big question.
Yeah.
Why even bother with cans? Like, what makes them worth all this effort?
That's a great question, and we'll definitely explore the advantages of cans in more detail later on.
Okay, good.
But I'll give you a quick preview. One of the most compelling things about cans is their efficiency. They can often achieve really good accuracy, sometimes even better than traditional architectures, but they do it with way fewer parameters.
So they're like the minimalist architects of the neural network world.
Huh. Yeah, I like that. Less is more.
And that efficiency makes them particularly attractive for applications where resources are limited. Like maybe you're deploying on a device with limited processing power or working with a small data set. Yeah, that makes sense. Okay, so we've got efficiency. What about interpretability? I remember we talked about how those spline-based activation functions can make cans a bit more transparent.
Exactly. With traditional networks, it's easy to get lost in all those layers and connections.
It's a black box.
Yeah, it really is. But with cans, you can actually visualize the spline functions. You can see how they're transforming the data.
So it's not just about getting the right answer, it's about understanding how you got there.
Exactly. And that can be crucial in fields where understanding the model is really important, like, say, scientific discovery or medical diagnosis. You need to know why the model is making the predictions it's making.
Yeah, that's a really good point. So efficiency, interpretability, it sounds like cans have a lot going for them. But let's be real, no model is perfect. What are some of the challenges that researchers are still facing when it comes to cans?
Well, like we said before, optimization is definitely a big one. Finding the right combination of hyperparameters and training techniques to make sure it all converges properly, it can be a real challenge.
A delicate dance.
Yeah, that's a good way to put it. And even with the best optimization methods, training cans can still be really computationally demanding, especially if you're dealing with these high-dimensional problems.
So scalability is still a concern.
It can be, yeah. And then there's the issue of noise sensitivity. Especially in their earlier versions, cans could be pretty sensitive to noise in the data, which could mess up their performance.
So they need to be a bit more robust.
Yeah. But the research is moving fast. Researchers are coming up with new techniques all the time to make them more robust and less sensitive to noise.
Well, that's good to hear. So it sounds like cans are a really promising approach, but there are still some kinks to work out.
Yeah, that's fair to say. But the potential is definitely there.
Okay. So we've talked about the architecture and some of the advantages of using splines, but I think it's time to dive into the math a little bit. What are the key equations that really define how cans work?
Okay, so it all starts with the Kolmogorov-Arnold representation theorem. That's like the foundation of it all. And remember, it basically says that any continuous multivariable function can be represented as a combination of simpler single variable functions.
Right. Breaking it down into smaller pieces.
Exactly. And that's where those splines come in. They're used to approximate those simpler functions. And we can actually express all of this mathematically.
So what does the equation look like?
Right. So a general CAN network, let's say it has L layers, can be represented by this equation. CAN X equals L1 composed with L2, composed with L3, and so on, until you get to A1 composed with A0, all of that times X.
Whoa, okay. There are a lot of symbols in there.
Don't worry, it's not as scary as it looks. Each error represents a transformation matrix for a specific layer in the network. But instead of having those weights like we see in traditional networks, these matrices are filled with the spline-based univariate functions that we've been talking about.
Okay, so those splines are really the key players here.
Yeah. And the X at the end, that's the input data that we're feeding into the network. So you feed in your input data X, and it undergoes all these transformations defined by those A matrices. Eventually, it spits out an output that's basically the approximation of the function you're trying to model.
I see. So it's like a chain reaction of transformations happening at each layer, all guided by those adaptable splines.
Exactly. And we can actually take this a step further and look at how each individual layer works. The equation for that is XL plus 1. J equals the sum from I equals 1 to NL of JIXLO.
Okay, even more symbols. Starting to feel a little lost.
No worries, I'll break it down. The S in that equation represent those learnable spline-based activation functions. Basically, it's saying that the output of a specific neuron in a layer, let's call it J, in layer L plus 1, is determined by summing up the outputs from all the neurons in the previous layer L. But each of those outputs from the previous layer is transformed by its own specific spline function, represented by...
Okay, so each neuron is taking in information from the previous layer,
Yeah.
but it's filtering that information through its own unique spline lens.
Yeah. And because we can adjust those spline functions during training, it gives CANs this incredible power to model super complex, nonlinear relationships, all while using fewer parameters than those traditional networks.
So it's like a really efficient way to capture those complex patterns in the data. But I know from our research that optimizing these networks can be a bit tricky. We've talked about things like gradient descent, but are there any specific challenges related to those spline functions?
Yeah, there are definitely some unique challenges that come with those splines.
Okay.
You see, those splines, they're really flexible, which is great, but it also makes the optimization process more complicated. It's like trying to herd a bunch of cats, you know? They all want to go in different directions.
I can see that.
So one of the things we have to be careful about is how we initialize the spline parameters. If we start with bad initial values for the control points of those splines, the whole optimization process can become unstable.
So it's like giving those cats a bad starting point. They'll just run off in all directions.
Exactly. And then there's the issue of training speed. Because CANs often have a lot of learnable parameters, the optimization process can be pretty slow, especially when you're working with high-dimensional data.
So even with those fancy gradient descent methods, training these networks can still take a while.
Unfortunately, yeah. But, you know, the field is constantly evolving. People are always coming up with new algorithms and optimization tricks to speed things up and make CANs even more practical.
Well, that's encouraging.
Yeah.
And I think it's important to remember the importance of regularization. We touched on it before, but I think it's worth emphasizing how crucial it is to prevent these highly flexible CANs from overfitting.
Absolutely. You don't want them to just memorize the data. You want them to generalize well to new, unseen data.
Exactly. So we need to strike a balance, right? Flexibility is great, but we need to make sure those CANs are learning the right things.
Right. It's all about finding the sweet spot.
Okay. Now, I'm curious about the different flavors of CANs. I know there are a bunch of specialized versions out there, each designed for a particular kind of problem.
Yeah, that's right. There's a whole family of CANs, each with their own strengths and applications.
So what's in this CAN family album? Can you give us a sneak peek at some of these specialized versions?
Well, for starters, there's the temporal CAN, or TCAN for short. This one is specifically designed for handling time series data.
So if you're working with things like stock prices or weather patterns or maybe even brainwave data, a TCAN would be the way to go.
Exactly. They're really good at capturing those temporal dependencies and making accurate predictions about things that change over time.
Wow, that's amazing. What else is there?
Well, there's also the Wavelet CAN, or WaveCAN. This one uses wavelet functions as its learnable activation functions.
Wavelets, huh? Those ring a bell. They're like mathematical building blocks that can represent signals at different scales, right?
Yeah, you got it. And by using wavelets, WaveCANs can capture both those fine-grained details and the big picture trends in the data, which makes them really good at things like image analysis and signal processing.
Interesting. So we've got TCANs for time series and WaveCANs for signals and images. What else have we got?
Well, there's also the graph CAN, or GCAN, which is designed specifically for working with graph-structured data, you know, like social networks or molecular structures.
So anywhere where those relationships and connections between things are really important.
Right. They're good at things like social network analysis, recommendation systems, even predicting how molecules will interact with each other.
This is all so cool. I can't wait to learn more about these specialized CANs. But before we dive into those, I think we should step back and compare CANs to the more traditional neural networks like MLPs, CNNs, and RNNs. How do they stack up in terms of performance, efficiency, all that good stuff?
Yeah, that's the big question, isn't it? And that's actually what we'll be tackling in the next part of our deep dive.
I can't wait. All right, welcome back to our deep dive into Kolmogorov-Arnold Networks. Before the break, we were just about to see how CANs compare to those big names in neural networks, you know, MLPs, CNNs, RNNs, the whole gang.
Right. Like, who would win in a neural network showdown? But before we jump into that, it's important to remember that All of these architectures, they have their own strengths, their own weaknesses.
Was it not really a one-size-fits-all kind of situation?
Not really, no. It really depends on what you're trying to do, what kind of data you're working with. But one area where CANs really stand out is efficiency.
Yeah, we talked about that before the break, how they can get some pretty impressive results using way fewer parameters. It's like they're doing more with less.
Exactly. And that efficiency leads to a whole bunch of advantages. For one thing, they often need less computational power, which is huge if you're working in an environment where resources are limited.
Yeah, like if you're trying to run a complex AI model on a smartphone or something.
Right. Or even on those tiny little sensors that are popping up everywhere, CANs could be a game changer for that kind of stuff.
Okay, so they're good in those resource-constrained situations. But what about speed? Do they train faster as well?
Yeah, usually they do. With fewer parameters to optimize, they can often converge much faster than those bigger, more complex networks. And that speed can be really valuable, especially if you need to iterate quickly or if you've got tight deadlines.
Yeah, time is money, right? So we've got efficiency, we've got speed. But what about accuracy? Can they really compete with the big boys in terms of getting the right answers?
Well, based on the research I've seen, they're definitely holding their own. In many cases, they can achieve similar or even better accuracy, and they do it with fewer parameters. It's pretty remarkable.
So it's not a trade-off between efficiency and accuracy. They can actually have both.
It seems that way, yeah. And I think a lot of that has to do with those flexible splines. They allow cannons to pick up on these subtle, nonlinear relationships in the data, things that other networks might miss.
So they're kind of like those detectives who can see the little details that everyone else overlooks.
Yeah. They've got a knack for spotting those hidden patterns. And on top of that, let's not forget about interpretability. We've talked about how those spline-based activation functions can make cannons a bit more transparent.
Right. It's like you can actually see what's going on inside the network.
Yeah. It's a big deal, especially in areas where it's really important to understand how the model is making its decisions, like in healthcare or finance. You don't just want to know the answer, you want to know why the model came up with that answer.
Yeah, it's about building trust and understanding. Like if a doctor's recommending a treatment, you want to know why they're recommending it, not just blindly follow their advice.
Right. It's the same with AI. The more we understand how these systems work, the more comfortable we'll be using them.
Okay, so CANs seem to have a lot going for them. Efficiency, speed, accuracy, interpretability. But I know no model is perfect. What are some of the areas where CANs might struggle compared to those more established architectures?
Well, one area where they can run into trouble is when you're dealing with really complex geometries or very high-dimensional data. In those cases, things like CNNs and RNNs, which are specifically designed to handle those kinds of patterns, they might still have an edge.
So if you're analyzing a huge image data set or trying to model some complex time series data, those specialized networks might still be the better choice.
Possibly, yeah. It's
Yeah.
like, sometimes you need a specialized tool for the job, not just a general purpose one.
Right. And then what about noise? We talked about how CANs can be sensitive to noise. Is that still an issue?
Well, they've definitely gotten more robust over the years, but noise can still be a problem. It's just something to be aware of when you're working with them. You might need to do some extra pre-processing of your data to make sure it's clean enough.
So careful data preparation is key. It's like laying a good foundation before you build a house.
Exactly. A solid foundation makes all the difference.
All right. So we've got to be mindful of the data, and we've got to be mindful of the computational resources. Anything else?
Well, training time can still be an issue. Even though CANs are generally more efficient than other architectures, optimizing those splines can still take a while, especially for larger data sets. It's something that researchers are working on, but it's still a consideration.
So it's like you gain efficiency and interpretability with CANs, but you might have to be a little patient when it comes to training time.
Yeah, that's a good way to put it. It's a trade-off. But like I said, the field is constantly evolving, so I wouldn't be surprised if we see some breakthroughs in training speed in the near future.
That would be awesome.
Yeah.
Okay, so we've talked about the pros and cons, the challenges, and the potential benefits of CANs. Now I'm really curious to hear more about those specialized versions we talked about earlier. T-CANs, Wave CANs, G-CANs. Can we dive into those a little deeper?
Absolutely. Let's start with T-CANs, those masters of time series data. What makes them special is that they've got these built-in memory mechanisms.
Ah, so they can remember past events,
Right.
kind of like those recurrent neural networks, or RNNs.
Exactly. But unlike RNNs, which can sometimes struggle to remember things that happened a long time ago, T-CANs tend to be much better at handling those long-range dependencies.
So they've got a better long-term memory.
You could say that.
Yeah.
And that makes them really good at forecasting, like predicting stock prices or figuring out how a hurricane might evolve over time.
Wow, that's impressive. Okay, what about those wave cans? The ones that use wavelets?
Ah, yes, the wavelet wizards. Remember how wavelets can represent signals at different scales, capturing both the big picture and the fine details?
Yeah, it's like having a zoom lens that can focus in on the tiny details and then zoom out to see the whole scene.
Exactly. And that's what makes them so powerful for analyzing things like images and signals. They can pick up on those subtle features that other networks might miss while still understanding the overall context.
So they're like those super detectives who can spot a tiny clue in a crowded room.
Yeah, they've got a real eye for detail, and that makes them really good at things like medical image analysis, where you're looking for those tiny anomalies that might indicate a problem.
So they could be really valuable for early detection of diseases.
Absolutely. Early detection is key. And then we've got the GKNs, those graph gurus. They're all about understanding relationships and connections.
Yeah, they're like the social butterflies of the neural network world.
Exactly. They can analyze those complex webs of interactions in graph data, like social networks or molecular structures. And they can use that information to make predictions about things like who you might be friends with on Facebook or which drugs might be effective against a certain disease.
That's amazing. So they're like matchmakers and drug discoverers all rolled into one.
Pretty much. They're really good at figuring out how things are connected and what those connections might mean.
This is all so fascinating. It's amazing to see how these specialized cans are pushing the boundaries of what's possible with AI. But before we get too carried away, I think it's important to pause for a moment and think about the ethical implications of all this. These are powerful tools, and we need to make sure they're being used responsibly.
I totally agree. Ethics is something we should always be thinking about when it comes to AI. We need to make sure that these systems are fair, that they're transparent, and that they're accountable.
Absolutely. We need to be mindful of potential biases in the data, and we need to make sure that these systems are being used for good, not for harm. It's a big responsibility.
It is. But it's also a really exciting time to be working in AI. We have the potential to solve some of the world's biggest problems, but we need to do it carefully and thoughtfully.
Well said. Okay, so we've explored the strengths and weaknesses of CANs. We've looked at some of the specialized variants. We've touched on the importance of ethical considerations. But I'm curious, where do you see this field going next? What's on the horizon for CANs?
That's a great question. I think we're just scratching the surface of what's possible with CANs. I wouldn't be surprised if we see even more specialized variants popping up, tailored to all sorts of specific domains and tasks.
So even more specialized CANs, like ones specifically designed for analyzing financial data or predicting climate change.
Exactly. And I also think we'll see more integration of CANs with other types of neural networks. Those hybrid architectures could be really powerful, combining the strengths of different approaches.
So we could have networks that combine the spatial reasoning of a CNN with the temporal memory of an RNN and the interpretability and efficiency of a CAN, all working together.
Yeah. The possibilities are pretty mind-blowing, and I think that's what makes this field so exciting. There's so much potential for innovation and discovery. It's an amazing time to be involved in AI.
Absolutely. Well, I think that's a great place to wrap up this part of our deep dive. In the final part, we'll explore some of the cutting-edge research that's pushing the boundaries of CANs even further. We'll also delve into some of the big questions about the future of AI and the role that CANs might play in shaping that future. Stay tuned. Welcome back to the final part of our deep dive into the fascinating world of Kolmogorov-Arnold networks. We've explored how they work, their strengths, their limitations, those cool specialized versions, all that good stuff. But now I want to look ahead. What does the future hold for CANs? Where is this all going?
Well, the crystal ball's a little fuzzy, but one thing's for sure, the future of CANs is bright.
Okay, good. I like the sound of that.
Yeah.
What specifically has you excited? What are some of the most promising areas of research?
One area that's really got people buzzing is the development of even more specialized CAN variants. We talked about T-CANs, Wave CANs, and G-CANs, but those are just the beginning, really.
Right. So we're going to see even more of these specialized CANs popping up, each one tailored to a specific kind of problem.
Exactly. Imagine CANs for finance, for climate modeling, for robotics, all sorts of things.
Wow, that's wild. It's like a whole family of CANs is going to emerge, each one with its own superpower.
It's pretty amazing. And I think we're also going to see more integration of CANs with other types of neural networks.
Oh, right, those hybrid architectures?
Yeah. combining the best of both worlds, so to speak. Like, imagine a network that has the spatial reasoning of a CNN, the temporal memory of an RNN, and the interpretability and efficiency of a CAN all working together.
That's a pretty powerful combination.
It is. And I think we're just starting to scratch the surface of what those kinds of hybrid networks might be capable of.
Okay, so more specialized CANs, more integration with other architectures. What about challenges? Are there any big hurdles that researchers need to overcome?
Oh, yeah, there are always challenges. One of the big ones is scalability.
Right, like as we start tackling more and more complex problems, working with bigger and bigger data sets.
Exactly. We need to make sure that CANs can keep up. Imagine training a CAN on a data set with billions of data points.
Oh.
Yeah, it's a lot. You'd need some serious computational power for that. So we've got to figure out ways to make CANs more scalable, more efficient, so they can handle those massive data sets.
Okay, scalability, what else?
Well, robustness is a big one too. As we start using AI systems for more and more things, it's really important that they're reliable, that they can handle unexpected inputs.
So if they encounter some noisy data or something that's totally out of left field, they don't just crash and burn.
Right. They need to be able to adapt, to keep functioning properly, even when things get a little messy.
Okay, robustness.
Yeah.
And then, of course, there's interpretability.
Yeah, that's an ongoing challenge for sure.
Even though CANs are more interpretable than some other architectures, there's still work to be done.
Absolutely. We need to keep developing better ways to understand how CANs make decisions, especially when they're being used for important things, like medical diagnosis or financial forecasting.
Yeah, high-stakes situations. We need to make sure we can trust these systems, and that means understanding how they work.
Right. It's not just about getting the right answer. It's about knowing why the answer is right.
Well said. Well, I think that just about wraps up our deep dive into Kolmogorov-Arnold networks. It's been a fascinating journey, and I'm honestly a little blown away by the potential of these things.
Me too. It's a really exciting time to be working in AI, and I think CANs are going to play a big role in shaping the future.
Absolutely. And to our listeners, thanks for joining us on this deep dive. We hope you found it as fascinating as we did. We encourage you to keep learning about CANs and all the other amazing things that are happening in the world of AI. It's a rapidly evolving field, and there are always new discoveries and breakthroughs to be made. So stay curious, keep exploring, and who knows, maybe one of you listening right now will make the next big breakthrough in AI.
Yeah, anything's possible. It's an exciting time to be alive.
Well, that's all for today, folks. Thanks for listening, and happy diving.